So I just wanted to expand a little bit on what you saw in the Ferris wheel video. So I've got this circle here, and over here I am going to graph the height of the Ferris wheel compartment as we go round the circle. And I'm going to turn the sine curve on. So you can see we've got the angle here, and when it increases slightly, the height is starting to increase, and I'm graphing that over here. So if I increase it a little bit more to 30 degrees, we know that sine is 30.6, but close enough. We know sine of 30 equals half from our exact value ratios, and you can see right there that's approximately half. If I go further up to 45, that's 1 on root 2. Sorry, I've got to drag it up here. So there we go, that's 1 on root 2 there, 0.7 something. And then I'll take it up to 60 degrees, which is root 3 on 2, which is getting quite close to 1 now. And then if I make the angle all the way up at 90 degrees, that height is now 1 unit, okay, up there. Now as I go around into the next quadrant, the height is reducing and coming back down, and when it gets over to 180 degrees, it's 0. Then the height goes negative, and it's increasing in the negative direction, increasing to -1 at 270. And then the height starts decreasing again as it comes down back to 360 degrees. Now I could keep going, and the curve would keep going. I could keep going to the left, and it would go this way. That curve goes on forever and ever with that pattern. That's the sine curve. Now I'm just going to refresh that, and I'm going to turn on the cosine curve. So remember, the cosine is the adjacent side, so that's the distance from here across. So at the moment you can see there's a point plotted at 1 because that distance is 1. So what we're doing is we're looking at the distance from this line to where the car is sitting rather than the height. So if I increase the angle a little bit, we're looking at this blue line here. That distance has started to decrease. At 30 degrees, it's going to be root 3 on 2, which we can see from our exact value ratios. And then 45, it's 1 on root 2. You can always put those in your calculator to see what they are as a decimal. At 60 degrees, it's half. At 90 degrees, that width is 0. So we're down here at 0. Then the width starts going negative. We know cos is negative in that quadrant. And it's exactly the same as the sine curve. But the same shape, I mean, as the sine curve. But it starts at 1, goes down and back up. And again, that keeps going forever and ever in both directions like that as well. Lastly, let's look at the tan curve. So remember, the tan curve is the sine curve divided by the cosine curve. So it's the ratio. But interestingly, it's also the distance up here. So if I increase slightly, you can see in green, this distance actually matches because we actually have a pair of similar triangles. So the sine over the cosine is equal to this height over 1. So this green height here gives us the tangent curve. And as I increase the angle, it goes up and up and up and up and up and up and up. At 90 degrees, it just doesn't work anymore because this height is not there anymore. So it's undefined at 90 degrees. Let's look at what happens when we go over 90. Also, just one thing about 90 degrees, because it's sine on cos. Cos is 0 at that point, and you can't divide by 0. So let's have a look at what happens. Now you can see it coming back up again. Make sure to look at this green line as well as this curve. I go around a couple of times. So going all the way around. So the green line now is down here in the negative. We're graphing over here. Now that shape again just repeats and repeats and repeats and repeats. So that gives us the tan curve. So I just wanted to look at drawing the trig curves by hand. So here's y equals sine x. So of course sine of 0 is 0. Sine of pi on 2 is 1. I normally just start by plotting these points. Sine of pi is 0, sine of 3 pi on 2. So remember here we're talking about the height in terms of the Ferris wheel. And I just start by plotting those points. And then it goes backwards as well. So I do the same thing over this side, like that. And then I kind of almost do semicircles. They're kind of close to a semicircle. So I start with this part, and then I go underneath. And then I go, normally, often we stop at 2 pi, but I'm gonna keep going. Now you can see on my page, I use 2 squares for 1 and 2 squares for pi on 2, and that tends to give us quite a nice shape. So going back the other way, if I'm joining those dots, that's how I get myself a fairly nice sine curve. Now let's do cosine. Now of course remember 2 pi is 360 degrees. So these are 90 degrees each, 90, 180, 270, 360, and so on. So let's do the cosine curve. It's exactly the same really, but we start up here at 1. So we've got 1, 0, minus 1, 0, 1, 0, minus 1, 0 would be there again. And we've got this nice smooth curve, etc. It goes back this way as well. So just like that. Now for tan x, it's slightly harder. So remember at 90 degrees or pi on 2, tan is sine over cos. Where cos is 0 up here, we're going to end up with an asymptote down here. So at pi on 2, there's going to be this asymptote. Same thing at 3 pi on 2 and 5 pi on 2, there will be asymptotes. So there's not one at 0, there's one here, and then we skip one. That's our next asymptote. And then we skip one, we go to this one, that's our next asymptote. And there'd be one over there as well. Okay, so I've drawn those asymptotes. Now tan of 0 is 0. That's one I like to put in straight away. I just sort of do it by plotting points. So tan of 45 degrees, right, or pi on 4 equals 1. And down here we've got minus 1. I just plot those 3 points really. Then I do this nice curve that heads up towards the asymptote, and the same thing down in that direction. And then we just repeat that across and so on. So you can see I repeated that over and over again. There's a nice tan curve. Graphing the reciprocal trig functions. So the first one is cosec x. So what you can see here is I've actually graphed y equals sine x. I'm using radians. So down here we're at 2 pi radians, which is 360 degrees. Now to graph cosec x, I need to do 1 over sine x. So we're really focusing on the y coordinates of sine x. So at this point the y coordinate of sine x is 1. Sine x equals 1 right here. So 1 over sine pi on 2. 1 over 1 is 1. Now when I'm down here where the y coordinate is half, then that's, let's do this side actually. So when the y coordinate is half, that's at 30 degrees or pi on 6. So 1 over half, 1 divided by half, equals 2. So I'm going to have a point right there. And that'll be the same over here. I'll have a point right there. Now, when the y coordinate is 0, 1 over 0 does not work. So at this point, I'm actually going to have an asymptote. So there'll be an asymptote right on that point. And there'll be another one over here at 2 pi. And another one here at negative pi. And of course there'll be one at 0. So anywhere where the sine curve equals 0, where the y coordinate is 0, 1 over 0 does not work. There'll be one at negative 2 pi. there'll be one at 3 pi. All of those places have now got these green asymptotes drawn to show that the sine curve, 1 over the sine curve, it just doesn't exist. Okay, let's continue plotting points. So just here, my y-coordinate here is a quarter. So 1 over a quarter is 4. Same thing over here, 1/4, 1 over a quarter is 4. So you can see that shape happening there. Now that's going to get repeated over here, where sine is equal to 1, we'll have 1 over 1, where it's equal half, 1 over half equals 2. So about there. When it's a quarter, 1 over a quarter equals 4. Here it's about half again, so 1 over half equals 2. So you can see a real shape emerging here. It's also going to be the same over at this point. So we've got there, we've got 2, we've got 4, about there and about there. Now let's look at these negative parts. So here the y-coordinate is -1, and 1 over -1 is -1. Here it equals -half, 1 over -half is -2. So you can see we've got the same pattern happening. Here at -1/4, 1 over -1/4 is -4. So we're right down here. The same thing over here. So -2 and -4 there. And this is going to repeat here, of course. So we've got points there, we've got points about there, and we've got points about there and there. Okay, let's have a look and see how well we graphed those. So I'm going to actually turn on the cosec curve. Now to graph cosec and desmos, you just type CSCX. Let's turn that on now, and there it is. So it looks like we did a pretty good job of plotting that. Now that keeps going forever and ever. If I zoom a little bit, it does ruin my dots, of course, but you can see, I'll just clear all the drawings, that happens forever and ever and ever. I didn't keep doing asymptotes further, but they are there. So just like with any asymptote, it's like gravity, where it pulls the curve towards it. So it's going to go up forever and ever and ever, but not quite touch the asymptote. Now I can do the same thing with cos x, which I'll do in a moment. I now have cos x graphed, and I've already actually put in these asymptotes. Anywhere that cos x equals 0, we're going to get an asymptote for graphing sec x. So remember, sec x is 1 over cos x. So we're going to see now that exact same shape that we just saw in the sine curve. So 1 over 1, 1 over half, 1 over a quarter. The only thing that is different is the curve is now centered around 0. So I'll graph those on top of each other in a minute. So we're going to get a point here, we're going to get here and here. We're going to get points there and there. So I am going to turn on the graph of sec x so you can see it is pretty much the same. Just got to, there we go. Okay, I'm going to draw them actually now on the same one. So I'm going to put cosec x back on. So you can see cosec x is drawn over there further. I'll actually just put sine x back on as well. So the green one is sine x. So this is cosec x. The red one is cos x. So this one is sec x, or 1 over cos. And that, of course, keeps going forever as well. Now, I'm now going to look at cot x, which, of course, is 1 over tan x. So I've got tan x drawn here. I haven't actually drawn in the asymptotes for tan x. Instead, I've drawn in the asymptotes where they're going to be for cot. So cot, instead of sine over cos, it's cos over sine is another way to think about it. Its asymptotes are going to be anywhere where sine x equals 0 or where tan x equals 0. So its asymptotes are going to be at these zeros, just like with the other ones. Now, in terms of graphing 1 over this curve, if we look at this point right here, we have the point where the tan x equals 1. So 1 over 1 is going to be 1. Up here, we have a point where tan x equals 2. So 1 over 2 is down here at half. Up here tan x equals 4, so 1 over 4 is a quarter, so just there. Over here tan x equals half, 1 over half is up there at 2. Down here tan x equals a quarter, so we're up here at 4, 1 over a quarter is 4. Down here tan x equals negative 4, so 1 over negative 4 is at negative a quarter. Here where tan x equals negative 2, 1 over negative 2 is negative half. At 1 we're at 1, at negative 1, sorry, we're at negative 1. Here where tan x equals a quarter, we're down here at negative 4. 1 over negative a quarter is negative 4, and there's our negative 2 in there where it's equal to half as well. So you can see that general shape. Now that shape of course is going to get repeated where the tan curve repeats. Now right here, the tan curve doesn't exist. So saying 1 over the tan curve there kind of doesn't make sense. But because we're now defining as cos over sine rather than sine over cos, cos over sine here would be 0 over 1, which is 0. So cot does exist at that point. So let's turn on the cot curve so we can see what it looks like. And there it is. So the blue one is cot x and the red one is tan x. So it's pretty much the exact same shape as tan, it's just been switched. Now practicing drawing these as much as possible is a really, really good idea, so that you really get to know these shapes well. You could be asked to graph any one of these in any exam. Now I'm going to go back and actually graph the reciprocal ones here as well and show you how I do those. So firstly for cosec, now remember in Desmos, that's CSCX, or you can just do 1 over sine x if you're in Desmos. So the first thing I tend to do when I'm drawing these is actually to draw on the asymptotes. So anywhere there's a 0, I'm going to need an asymptote. So by the magic of television, I've now drawn on all my asymptotes at all the zeros down the page. Now, if you're asked to graph one of the reciprocal functions in an exam, I would always start by just lightly drawing the original function. So rather than memorizing these shapes, they really do need to be compared with the original function. So here's my sine x. So to draw my cosec x, I'm literally just going to do this. Every single point towards my asymptotes and being lined up nicely on my 1s and my -1s. As long as you've got that general shape, you should get full marks in an exam. So that would be the same for cos x, except here's my 1s slightly further over. So I've drawn all those ones for sec x on there. And that's how I draw those. I draw cos first and then put those sec x ones on. For tan x, again, the first thing I'm going to do is draw my asymptotes. So those are in pink, so they're different from the tan asymptotes, but they're still the same distance apart. So there's still this big 180 degree or pi gap between asymptotes. So from pi and 2 to 3 pi and 2, that's a gap of pi. So the asymptotes separate by pi. And then I mark my 1s. Okay, I know that it's going to actually be 0 there where the asymptote was for tan, and then I just draw just like drawing a tan curve like that. So I'll just do another one, 0 right there, 1 and -1, and then just that nice curved shape. Just be careful to make sure it is curvy and not a straight line. Now let's talk about the language around these curves. So these are periodic functions. They repeat with a period. The period is the length of one cycle. So in terms of the sine curve, the distance from there to there is one period because it repeats after that into a second period. The amplitude is the height from the center to the peak. So the center on this one is the x-axis. So right here is the amplitude. And I've put P for period, A for amplitude there. So A, P. Okay, So for sine x and cos x, for both of those, the length of the period is 2 pi radians. You can say 360 degrees also, but one period is 360 or 2 pi, and then it repeats again. The amplitude of each of those is 1, because remember, this is 1 and this is minus 1. 1 minus 1. This is 2 pi, 2 pi. So the amplitude for each of those is 1. The center for each of them is the x-axis along the middle there. So it's the x-axis, and remember, of course, the coordinates of that is y equals 0, the equation, of that line. Now let's look at the domain and range of each of those. So the domain is that we can do anything from negative infinity to infinity for x. The range goes from -1 to 1. It includes -1 and 1, of course. So I'm using square brackets, round brackets for infinity. Now let's look at tan x. So the period of this one, so remember that there is pi on 2. This is negative pi on 2. So half of pi there, half of pi there. The total period is pi, or 180 degrees. Okay, the distance from there to there before it starts again. The amplitude for this one, not applicable. There isn't one. You can't say amplitude. It goes up to infinity. The center for this one is the same as the others, y equals 0 along the x-axis. Now the domain for this one, I'm going to write this a little bit differently because it goes on forever. So it's not equal to pi on 2, and then another pi further along is 3 pi on 2. It can be negative also, so plus or minus for each of those, plus or minus 5 pi on 2, etc. That goes on forever and ever in that pattern. So I've written, that's not our interval notation. It's a bit tricky to write it with interval notation. The range for tan does go from negative infinity to infinity. You can also be asked to work those out for the reciprocal functions, and I'm going to leave that for you to work out on your own.